Sure.
Right there in the
I have no authority. Is that okay?
No, it's
okay.
it's more for my company to know I was actually here and actually worked on the
Okay.
machine.
Do you want my name here too?
No, it's
okay. All right. Thanks. Okay, so before we get started on the new stuff on stereochemistry, there's a question about the quiz. Sounds like a couple people had. So what do you do with a molecule like this? So let's say you have this molecule on the left, and you want to know what its conjugate base is. In other words, if some base, we're calling B here, if some base were to deprotonate this molecule, were to take one of the hydrogens off this molecule, what would be the resulting molecule that you would get? And so the question really is, because we don't know the pK of the base, but we know that one of the hydrogens on this molecule on the left is going to be more acidic than the others. That's the idea here. There's actually, even though there's only 2 shown hydrogens on this molecule, there's actually many hydrogens, right? All the ones connected to the carbons. So potentially, any hydrogen could be deprotonated by a base. But if we look carefully at a molecule and we think about what we know about acids and acidity, we can probably guess which hydrogen is going to be more acidic than the others. And that's another way that we can use our Pka table. So if we go back to the book here, we look at chapter 2. Yeah, I got to post a little bit better Pka table, but this one will do for this one. So page 45. All right, so we look at our Pka table. And yes, these are pKa's of individual molecules, but we can use this as an analogy to our molecule. So we can look at our molecule and say, okay, what types of hydrogens does it have? What types of functional groups are the hydrogens in this molecule like? So the first ones to look at are just like the regular hydrogens coming off of carbons. We might refer to those as alkane hydrogens. Like they're just like any other alkane. They're CH, just like any other CH thing. All the hydrogens around there. So if we were to guess, if we were looking at a pKa table, if we wanted to guess a pKa, we would compare this to something like ethane, because it's a carbon hydrogen with no other functional group. So we would say, okay, the pKa's of those hydrogens are probably around 50. Maybe a little less because of the inductive effect of the carboxylic acid, but around 50. Okay, so what other types of hydrogens do we have in this molecule? Well, we've got this one and we've got this one, which are clearly different from the alkane hydrogens. This one, so the bottom one here, what would you say that is more like? What kind of a functional group is that? The bottom one, yeah. An alcohol, right? So that's an alcohol. So that's going to be fairly similar to any other COH type thing. So we could look at our pKa table. We'd find the alcohols. In this case, we can look at like methanol. Ethanol is here. Ethanol's pKa is about 16. One good thing to just kind of remember is alcohols are similar to water. So alcohol pKa is about the same as water pKa, which is right around 16. So if these are around 50, then this one is going to be around 16. We don't know exactly what the pKa is because every molecule is a little bit different. But in general, similar functional groups are going to have the same pKa's. So that one's about 16. And then our last one up here, what kind of a functional group is that? Remember what that's called? It's not just an alcohol. It's something else. Yeah, it's a carboxylic acid. So again, to find the pKa of that, we're going to look at our pKa table and compare it to other carboxylic acids, like acetic acid, benzoic acid. Those are both carboxylic acids, because we can see they have similar functional groups there. So those are all right in like the 4 to 5 range. So we have general idea. We have a general idea of the pKa's of the different hydrogens in this molecule. So if this is going to react with only one base, which hydrogen is the base likely to grab? Yeah, the carboxylic acid one. Right? It's going to take the most acidic hydrogen. So this hydrogen gets the award for most acidic in this molecule because it has the lowest pKa of all the different types of hydrogens. And so if there's only one base, that's the one it's going to grab. And so the product then of the deprotonation is going to be this, right, with the byproduct of HB. So the base grabs the hydrogen off of the carboxylic acid, but doesn't grab any of the other hydrogens because they're not acidic enough. So the base is only going to take the most acidic hydrogen. So in larger organic molecules, you can look at the different hydrogens around the molecule to find different pKa's, and then whichever one the base takes is going to be the most acidic is the one that the base is going to take off.
If you would have then mixed it with some acid, would then the alkane have been part of that?
No, so that's a different question then, because so then we're looking, it's a good question though. So let's look at it again. Well, actually, for the specific molecule it would be difficult, but so the question is, what if you take this molecule and instead you mix it with an acid instead of a base? So now you're looking for the most basic spot on the molecule, which would be the one that is the least acidic when it gets protonated. So after the extra hydrogen is added, it should have the lowest pKa. So in that case, it's going to be one of the oxygens, like one of the lone pairs on the oxygens. And which oxygen it is, we have to get more detailed pKa tables to find that. It's going to be this bottom alcohol, but for other reasons that we haven't really gone into. That's a good question. So there's a question on the quiz, not exactly this one, but same idea. You have multiple different potential deprotonation spots in a molecule, and the question is asking which hydrogen is going to come off and which conjugate base are you going to get. So it's the same logic, same idea. You compare the pKa's of the different hydrogens, and the more acidic hydrogen is the one that's going to come off.
So then that on the right is the conjugate base?
Right.
And the one on the left is the acid?
Right. So does that give you a clue for that question? No, this is the conjugate base. Well, HB is the conjugate base of B, but the molecule is the conjugate base of the first molecule. Yeah.
What if I had a molecule that was amphoteric?
Right.
And I wanted to make it a conjugate acid? Then I would just do the same thing. I would just take off the most basic?
Well, think about what that means. So yes, but if you're making an acid, that means you're adding a hydrogen, right? So if you're adding a hydrogen, if it's acting as a base and it's going to grab a hydrogen, then you need to find the most basic spot, which is the opposite of the table. So let's say you're comparing an OH versus an NH. And you want to know not which one is more acidic, but which one is more basic. So in that case, you're looking at hydronium versus ammonium, because those are the two conjugate acids. And if we look on the other side of the table here, that means the stronger base is ammonia and the weaker base is water. Because stronger acids always go with weaker bases. You'll have a pKa chart on the test, yes.
So at the tutoring center, kind of what he told me was to
Uh-huh.
think of it as like a proton hydrogen,
Mhm.
plus a couple of like lone electrons, and then just move the electrons over. You can clear up those and then the hydrogen, right? So does that sound right or no?
Maybe. So the electrons are on the hydrogen or they're on...
Yeah, because like in the example that we had used, it was acidic acid and ammonia, and the two lone pairs on the nitrogen move over to the acidic acid.
Yeah, so grab the lone pair on the nitrogen grabs the hydrogen.
Yes, but then
Can I see what you've got
the
there?
conjugate also end up with like the electrons? Because this was the one that you had said, right?
Right.
I got you. And this ends up keeping the
Yes.
electrons in the hydrogen.
Right.
Here.
Right.
To separate them is
Yeah, pretty much. There's going to be an acid that has the hydrogen, and there's going to be a base that has a lone pair. Yeah, that's how it's going. There might not always be a nitrogen. Could be other things, but yeah.
So I want to add a hydrogen to make a conjugate base, and I want to subtract a hydrogen to make a conjugate base.
No,
I want to add a hydrogen to make a conjugate acid, and subtract a hydrogen to make a conjugate base.
yeah. Think again about the definitions. Acids are molecules that can give up hydrogens. So anything that we call an acid is going to be the thing that has more hydrogens generally, more to give up. And the base is going to be the thing that can accept the hydrogen, so it's going to be the thing, we might say, missing hydrogen. Is that helpful? Not more confusing? Let me know if these questions keep coming up and what you need, and we'll go through them.
So the structure that's the conjugate base, the other one on this side would be the conjugate acid.
Conjugate acid, conjugate base, conjugate acid. There's always going to be two pairs, and they only differ by that hydrogen.
Oh, okay.
So the hydrogen moves away from the acid to the base in both cases, or yeah.
Alright, now I gotta ask one more.
Okay, go ahead.
Okay. So subtract the hydrogen to make a conjugate base, and I do that by finding the weakest acid, right?
Strongest acid.
Strongest acid,
Yeah,
and taking that one.
right.
And so if I reverse it and I add a hydrogen to make a conjugate acid, then I do that by finding the strongest base
Yes.
and taking that one.
Yeah. So maybe we should talk about that again. I mean, that's correct. But let's look at it the other way, because we didn't really talk about evaluating base strength. So let's look at base strength. So let's say you've got two different types of bases. You've got, and let's look at neutral bases, because those are sometimes a little trickier. Okay.
I find it really helpful for you to ask for definitions before the problems.
Okay.
Because then it gets you thinking about how you're
Sure.
going to work the problem. Like the first two is helpful,
That-
having to define before it works them.
Okay, good. That's something that you can take forward as just a strategy in general, that if, whenever you're looking at a problem, think about
Right.
what do these things actually mean? Okay, that means that means that. Okay, now I can try to do the problem.
Right.
Yeah, it's a good idea. All right, so let's say we've got these two molecules, and we want to know, so the opposite of the previous question, we're going to react this with some hydrogen, and we want to know, let's say we've got like, actually let's put these in the same molecule, so we can compare them. So here's our molecule. We're going to add a hydrogen, and we want to know, where is that hydrogen going to go? Is it going to go to the OH on the left, the alcohol, or is it going to go to the OH on the right, the ketone? That's the only real choices here, right? The hydrogen's not just going to stick onto a random carbon somewhere because the carbons are already all set up. So let's actually draw those two products and then think about how we would decide which one is more likely to occur, or which one's going to happen first. So if we protonate on the ketone, we'd add the hydrogen on the alcohol and would have a formal positive charge there on that alcohol. All right, so those are the two different possible conjugate acids. So is everybody good so far of how we get from the left to the right? And these are possibilities. We're not saying it's going to make both of them. We want to know which one is which, or which one is favored. One of those is going to be a little bit better than the other, because one of those sites on the molecule on the left, on the starting molecule, is more basic than the other. Either the OH or the O on the carbonyl is going to be more acidic, or more basic, sorry. We don't know which one yet. Okay, so the way we judge that, we have to be careful. We can't just look these things up in a standard pKa table, because a pKa table is generally listing acids. So it's listing the things that are getting deprotonated. Those are the pKa's we're looking up. So what we really want to do is we want to look up these molecules in a pKa table, or these similar molecules in a pKa table, because those are the acids in this reaction. This was acting as a base, and now we're making acids. So we want to go find in a pKa table, and I think the book is not, this one is not good enough for this, so we'll have to find another one. We'll go look for it together. But we want to look at what is a pKa of a protonated ketone versus what is the pKa of a protonated alcohol. So let's see if we can find those pKa's somewhere. So the big like massive pKa table is this one from David Evans at Harvard, which is a very large document, 6 pages of pKa's, used all over the place. And I think we're going to be okay right on the front here. So let's take a look over on the right at some protonated species, because that's what we've got. All right, so a protonated alcohol. So this is going to be similar to a protonated alcohol. If you see this, I don't know if you can see my cursor there. It's like the Me means methyl. So this is a carbon connected to an OH, or an alcohol, that now has an extra hydrogen. And its pKa is about minus 2.2. So that's going to be similar to our protonated hydrogen. Let me make this bigger so we can see it a little bit better. All right, so we're comparing to this one here at 2.2. An alcohol with just one carbon connected. So that's probably a pretty good match for what we've got here. So we're going to say that this pKa over here is minus 2.2. Now let's find a protonated ketone, or a protonated carbonyl. So up here we've got some protonated carbonyls. And probably our closest match here is going to be the third one down, because the top one's a nitrogen. The next one's definitely a carboxylic acid, because it's got OH and OH. The next one down, that's our ketone. So pH means phenyl, so the benzene ring, so it's a little different from what we've got, but it's still the closest match that we can find. So we've got carbon on both sides, we've got a ketone, and our pKa is minus 6.2. Okay. Yeah, they got some. There's coffee spilled underneath, and it's like boiling on the hot plate. All right, so now we've got those two pKa's. We looked them up. And so what does it mean that the top one has a lower pKa than the bottom one? Right, that the top pKa, not the lowest magnitude, the lowest actual pKa. Okay, so we've got a stronger acid, weaker acid. So then we should be able to answer the actual question, which is, which spot is bound to be protonated. Which one are you going to make? Are you going to make the stronger acid, or are you going to make the weaker acid preferentially? So remember what, yeah, so let's look at this. The answer is, I'll tell you the answer, and then we'll go through and talk about it. The answer is that this one would be favored. Okay. The weaker acid is favored. We always think about weaker acids, weaker bases as being more stable. So it's going to go to the one that's more stable. The other way we can think about that is going back to our original molecule here, and we can say that this site here at the alcohol is more basic because it leads to the less acidic conjugate acid. Remember that conjugates are always opposite in strength. So if you have a weaker acid between the two, you have a stronger base. The stronger acid gives the weaker base. So the bottom one is favored because the alcohol is more basic. And we can also say that we figured out the alcohol is more basic because we looked at the pKa's of the protonated species and found the weaker acid. All right? So as you're doing your work, if you need a better pKa table than what's in the book, I just Googled pKa table, and it was that very first link was that nice big pKa table. You won't have one quite that detailed on the exam because you don't need it, but we'll have like a adequate one for whatever's on the exam. You're doing homework when you go. I'm glad to see that you're all working on the quiz and not saving it for tomorrow night. That's nice to see. Good job. Okay, that's fine. I mean, there is plenty of time. And personally, for me, I'm a procrastinator, so I'm always like the night before. But you will do better if you give yourself a little more time to think about it and work on it and evaluate it and ask questions and come in and ask about it. It'll go better for you. Okay. So back to stereochemistry. So last Wednesday, we talked about assigning absolute configuration and looking for stereocenters in these molecules. So let's do a quick review on that before getting in. All right, here's a molecule. I want you to assign the absolute configuration of that stereocenter in that molecule, of the one stereocenter in that molecule. Assign the configuration, RRS. It's called absolute configuration. All right, everybody got it? Not quite? Still working? Okay, keep going. All right, you got something, right? Close? Okay, so I will tell you that this molecule is, let me make sure I got it right. Okay, it's S. Did you get S? S, maybe? R? If you got right, R, you're half right. It's not true, no. It is S. Let's look at Y. So first thing we do is we assign the priorities of the groups. In this case, the OH gets the top priority because O beats carbon. Then we've got a hydrogen, which is going to get the last priority. Then we've got two carbons. One of them is part of a double bond, and one of them is not, so the one with the double bond gets the higher priority. Okay. Then comes that tricky third step, or second step, whatever it was, where we have to make sure the fourth group is in the back. So if the fourth group is in the back, that means we either need to flip this whole molecule over to put the hydrogen in the back, or do it this way and then flip what we get. So if we do it this way and flip what we get, we go 1 to 2 to 3. That's like a right turn, but the hydrogen's in the front, so that makes it S. If the hydrogen were in the back, then it would stay R. Yeah, so let's flip this whole thing over and see what we get. And I'll show you it works both ways. So we'll flip this whole molecule. Let's go like this way. If we just sort of like flip it over like that. Is that hard to see? That's probably harder to see. Let's do it this way. All right, so we're going to take the whole molecule. We're going to flip it 180 degrees. If we do that, we get this. We don't get the mirror image. We're not taking the mirror image. We're flipping it. The mirror image would be the opposite. And then we can do our priorities again. 1, 2, 3, 4. And you can see 1 to 2 to 3 is a left turn. So it's still S. So either way you do it, it works. You do have to be really careful. If you're going to do the flipping, it can be easy to get a switch by accident because you're not thinking about which thing is going to which side. So if you're going to do the flipping, I recommend, if you have models, make a model, or if it's a big thing where it's going to be annoying to make a model, another thing you can do, especially in practice, is just draw it on a piece of paper and then flip the paper over and hold it up to the light and like draw it that way so you can actually see what it would look like flipped over. But you do still have to watch the front and back. Like the front one's going to go to the back when it's flipped over, and the back one's going to go to the front when it's flipped over. All right. So let's look at molecules that have multiple stereocenters. The fun thing about molecules with multiple stereocenters, of course, is they can have multiple configurations, and then there are multiple different possible stereoisomers you can have. So let's look at this molecule. So this molecule has 2 stereocenters. And the other thing we notice here, the other little shortcut we're going to start taking now, is to not necessarily draw the hydrogen on the stereocenter. Because we still know it's there, because of the rule of 4 with carbon. Carbon needs 4 bonds. And we also know whether it's on a dash or a wedge, because there can only ever be 1 dash or 1 wedge. So if we look at the carbon where the bromine's coming off, the bromine's on the wedge, so that tells us we know the hydrogen's going to be on the dash. You're welcome to draw it in if you want, but we don't need it drawn out explicitly. It's there. The hydrogen on the other stereocenter with the OH we know is coming out at us because the OH is going back, so the hydrogen has to be coming out. All right, so now this molecule has 2 stereocenters, and because of that, it also has some more stereoisomers than before. So we talked about enantiomers. Enantiomers are exact opposites. So if we flip the stereocenters like this, Those two molecules are enantiomers of each other. Because they are complete opposites. They're total mirror images. They're non-superimposable mirror images because of their stereocenters. But there are two more stereoisomers of this compound that are not enantiomers of these two. And they result from only changing one stereochemical configuration. So let's say we leave the bromine alone, but we flip the OH. Or we leave the OH alone, but we flip the Br. Whoops. That's not what I said.
What does your right word say?
Enantiomers. Sorry, that's the same one. I'm drawing the opposite thing that I'm saying. It's confusing myself. Let's try that again. Okay. So all of these four are all different stereoisomers of each other. Right? They're all connected in the same way, so they're not constitutional isomers, but they have different configurations. So enantiomers are complete opposites. So the bottom pair is actually another pair of enantiomers. But now we need a new word to describe the relationship of like the bottom two to one of the top ones. So like what are these molecules to each other here? Yeah, these are diastereomers. Uh-oh, what happened? There we go. Diastereomers. Do I need to plug this in? Let me see here. Okay, so diastereomers are stereoisomers that are not enantiomers. So stereoisomers is every kind of isomer that only differs by the orientation in space. So R versus S, E and Z, whatever, those are all stereoisomers. Enantiomers are non-superimposable mirror images. Diastereomers is all the other types of stereoisomers. So E and Z stereoisomers are technically diastereomers, as are these other ones. So any relationship between two of these that is not a complete mirror image is a diastereomeric relationship. Those are diastereomers.
So like A and D would also be a diastereomer?
Yep. So maybe we should use a different color here. So these are diastereomers. These would also be like every other relationship here besides the two enantiomer relationships is diastereomers. So like this one and this one and this one and this one. Those are all diastereomer relationships. Yeah.
All diastereomers are going to be B or C?
No, they're going to be any kind of stereoisomers that are not enantiomers. So in this case, they're not E and Z. This is all R and S. This is all sp3 carbon. Enantiomers, as we talked about last week, have pretty much identical physical properties. They're very hard to separate. They have the same melting point, the same boiling point, because they're just mirror images. So all the structural relationships are going to be basically the same. Reactivities are the same, things like that. Diastereomers are usually not. So if you think about like polarity of these molecules, so the major polarity part of this molecule is going to be the OH, but the bromine might contribute a little bit to that too. If you look at the two enantiomers, they're total mirror images, so their polarity is going to be the same, just in like opposite directions. But the diastereomer is like, if you have the Br and the OH on the same side of the chain versus one on each side, that's definitely going to change the physical properties. It's going to change how it packs in the solid state. It might change its melting point, therefore, all that kind of stuff. So diastereomers can often be resolved, like you can purify your substance through recrystallization or chromatography and actually get the different enantiomers, or get the different diastereomers fairly easily. Whereas enantiomers, that's really tricky. Like we did GC, gas chromatography last week. Most standard GCs, you cannot separate enantiomers, but you can separate diastereomers because their boiling points are different. You can get very special columns, those tube things, that are actually chiral columns that preferentially pass one enantiomer over the other. Those are expensive and have various issues sometimes of working or not. But diastereomers are different, have different properties. Okay, so that leads us to our special kind of diastereomers called mesocompounds. So let's look at this molecule. So this is 1,2-dibromo cyclohexane. And its mirror image, or its enantiomer, is also 1,2-dibromo cyclohexane. So that tells us we need a little bit more information here on the name. So if we number this 1, 2, 3, 4, 5, 6, we can specify the stereochemistry of the two stereocenters. So number 1, carbon number 1, is that R or S? Yes, that one is R. And what about number 2? S, right? Yep. So we've got 1R, 2S, 1,2-dibromocyclohexane. That's how we add the stereochemistry to the name, just like we did with the double bonds. You use parentheses, and they go before the numbers, and you still have to put the numbers in, the location numbers. So we've got 1R, 2S, and now we want to draw its enantiomer, which is 1S, 2R. Now we can either just draw the direct mirror image, or we can flip both of the stereocenters. Those molecules look very, very similar, but they are not superimposable. Think about it. If you took one and tried to lay it on the other one, the bromines would not line up. Even if you flipped it over, they would still not line up. If you don't believe me, build a model, you'll see.
Why don't we call it 1R, 2S, cis, 1,2-dibromine? Like, why does cis and trans not matter anymore?
Good question. So cis and trans are not good enough anymore for chiral compounds because these are both trans. You see that? They're both trans-dibromocyclohexane because one bromine is up and one bromine is down. But they are still not the same molecule. So the designation of trans for this particular molecule is not specific enough anymore. And so we need the S and R to really say which one we're talking about. There are many molecules, many cyclohexanes that can be named with trans or cis because they're not chiral, and we'll talk about that in a second. But this one, those are actually different molecules, and so we can't just say trans or cis there. We have to use the stereochemistry.
Chiral molecules, cis and trans don't count.
Well, I wouldn't say they never count, but you have to look at the individual molecules and decide if that's a specific enough designation or not. As with the double bond, you can't go wrong if you do RS or EZ. So if there's any question, it's best to just not use cis and trans. Sometimes it's convenient, but it's never necessary, and it's always more precise to use RS or EZ. Okay, so these two are enantiomers. And we can also draw a diastereomer of these compounds. If we try to do like what we just did before and make a matrix of 4 things, of 4 structures that are all stereoisomers of each other. Whoops, sorry, that's the same one again. We could draw this one. And we could draw this one. Wait, this is wrong. Sorry. We messed this up. I knew something seemed weird here. That second one should be S and then R. Sorry, R and then S. We forgot to flip it, because if you look at number 2 here, 1, 2, 3, that looks like S, but the H is in the front, so we got to flip it, so it's R. So this should be 1R, 2R, this should be 1S, 2S. Sorry about that. Okay, so we made these diastereomers. Do you see, what do you think is the relationship between the one on the left and the one on the right? Are they enantiomers? What do you think? They look like opposites. So these are actually not enantiomers. Why are they not enantiomers? What are they if they're not enantiomers? They're not stereoisomers, actually. They're not those either.
Are they the same thing?
They're the same thing, yes. So if we were to flip this over, let's flip it over vertically. If we imagine, okay, so the bromines are going back. If you flip that whole thing over, where are the bromines going to be? They're going to be coming out front, right? So if we flip the whole thing over, we get this. Which is the same, right? The 3 arrows, congruent, exactly the same thing. So what does that mean? Because those two are mirror images of each other, but they're also the same. So what happens if your mirror image is the same as the original? Is it chiral? Achiral, right. If the mirror image is not different anymore, then that's actually achiral. It is no longer chiral because now its mirror image is the same thing. It has a superimposable mirror image instead of a non-superimposable or superposable mirror image. So we took a structure that has stereocenters, and this molecule still has, whoop, why did that move? This molecule still has 2 stereocenters, but it is no longer chiral. And that's called a meso compound. A meso compound has stereocenters, so it has carbons that have 4 different things attached and can be assigned R and S, but it is achiral instead of chiral because the mirror image is the same. And there's a relatively easy way to check for these things. And the way to check for it is to look for a plane of symmetry inside the molecule. If you look at this molecule, you can imagine cutting it in half and having mirror symmetry on either side. And that's the clue that this is a meso compound. So meso compounds occur when the symmetry of the molecule is such that when the stereocenters are in a particular configuration, that it now has mirror symmetry throughout. And if it has bilateral mirror symmetry, like people do, it can't be chiral, because its mirror image is always going to be the same. Okay. In the context of like an exam or something, or just looking at compounds, if you suspect, or in order to suspect that there might be a meso compound, look for symmetry. If you've got a molecule that kind of looks the same on both sides, has basically the same stuff attached, then there's a good chance that one of those stereoisomers is going to end up being a meso compound. If it's clearly very different, like the ones up here, where one side had a Br, the other side had an OH, there's never going to be like a way you can cut that in half and have it be the same thing, because it kind of looks different. So just be on the lookout for that. Yeah. Right, so that's what gives it, because here it looks symmetrical, but it doesn't actually have bilateral symmetry because the Br is up here and it doesn't have a counterpart to reflect to on the other side of the molecule. So these two are still chiral. These enantiomers are chiral, or these diastereomers, but this diastereomer is achiral because now it does have that symmetry. So yes, everything has to be in 3 dimensions reflecting on each other in the same way.
What is the name of the bottom one?
What?
What is the name of the bottom one?
Oh, yeah, so that's kind of how I knew that those first names were wrong. So this one is 1R2S. And the reason that you know that that's meso, or that has that symmetry, is we could also call that 1S2R. It's the same thing because it doesn't matter where we start our numbering. Because we could number at the upper right, where we started originally, or we could start our numbering at the lower right and go the other direction. We could also be looking at it from the front or from the back, and we always get S and R. We always get one S stereocenter and one R stereocenter. So it's also okay to call this 1S2R, because it all depends on how we start our numbering. So the book would actually call this, because of that confusion, often, and just to make it clear, often these things are named with just meso instead of the numbers. The numbers are still okay, but because it could potentially be confusing in like a search engine, or if you're looking up a compound on a specific something or other, if you just know you're looking for the meso stereoisomer, it's easier if you can just type in meso as part of the name instead of the 1 and the 2, which might be flipped. So then, of course, there are molecules with many different stereoisomers. So the more, there's actually, the book talks about it. You don't have to remember this, but there's this 2 to the n rule. Anytime you have 2 choices and you have a certain number of those choices, if you want to look at the different possibilities, that's 2 to the n. So if you have 2 stereocenters, 2 to the 2 is 4 different possible stereoisomers. 2 to the 3, if you had a third stereocenter, now you've got 8 different stereoisomers. 2 to the 2 cubed is 8, and so on. So it goes up very quickly. As you get to larger molecules, you can have a lot of stereochemistry, and that, of course, makes everything difficult with synthesis and whatever. So just quickly, the way that we look at stereochemistry of larger molecules, yes, we can still talk about the RNS and everything, but especially with natural products, it's often easier to do it experimentally, or more practical to do it experimentally. So what you can do, I'm just going to show you the picture here. One interesting physical effect that chiral molecules have is the rotation of plane polarized light. What that means is you have a light source, and you know light's a wave, right? Kind of going like this. Well, that wave can be oriented in any direction around 360 degrees. It can be going like this, and one of them could be like this, or this, or whatever. So if you have a polarizer, what that does is it filters out all the light that's not going in a particular direction, that's not oriented in a particular direction. Like polarized sunglasses, if you've ever seen that, that's what they do. They filter out the light, so only light oriented in a specific direction gets through. So you take that plane polarized light, and you pass it through a sample of a chiral molecule, a chiral solution, and what happens is it rotates the plane polarized light. So the light interacts with the molecules and ends up tilting to a different angle, and then you can measure what the angle is when it comes out the other side. So no matter how many stereocenters a molecule has, as long as it's chiral, you can figure out how much the light has rotated in one direction or the other. And you can measure that angle. And the interesting thing about enantiomers is the enantiomers will rotate light the exact same magnitude but in opposite directions. So one enantiomer will rotate the light to the right, and the other one will rotate it to the left. So when you talk about experimentally dealing with enantiomers, if you can see this here, rather than describing RNS, especially for very large molecules, we instead say plus and minus. And so if you see anything about stereoisomers with plus and minus, that's the experimental determination of stereochemistry, what it's actually doing to this light. And the only important thing really to remember about that, I mean, I'm sure there's lots of important things, but the useful thing the thing that'll be useful for you to remember is the plus and minus, the experimental determination of stereochemistry, do not correlate to R and S. So the R and S that we assign by looking at the structure have nothing to do with what this is actually going to do with plane polarized light. And the book actually has kind of a, well, their example shows, so their example here with butanol, the S is plus and the R is minus, but that is not necessarily the case. Every compound is going to be different. Another experimental term that we use a lot is racemic mixture. A 50-50 or an equimolar mixture of enantiomers. As we'll get into the next chapter, we'll look at reactions that produce stereocenters. So you start with something that's achiral, and you produce a stereocenter as a result of a reaction. But generally what you're going to do is produce a 50-50 mix of the two possible enantiomers. Because there's not, with the reactions we're going to look at, there's not a good way of controlling which side the particular thing is going to add on, so you're going to end up getting the R and the S. And that's called a racemic mixture. And that's generally what you'll get is these products, unless you do very special chemistry that allows you to pick one stereoisomer over the other. All right. So that's stereochemistry. You got it? Maybe? Okay, so the major goals of this chapter are finding stereocenters, looking for chirality, right? Assigning configuration, R and S, looking at diastereomers and assigning relationships. Are these enantiomers? Are they diastereomers? Are they the same? We're going to do one more little challenge to see how creative you can be in your problem solving. Yes.
Alright, so back when we were doing the ENC stereoisomers,
Mhm.
you gave us one that was like 2-bromo 1,3-cyclopentadiene.
Mhm.
And you said it doesn't get an E or a C because it's a cyclo.
Yeah.
Pentadiene, would then that get an R or an S?
Only if it had a stereocenter in it. Does it have a stereocenter?
Yes, bromo.
So say the molecule again.
It was 2-bromo 1,3-cyclopentadiene.
Diene.
Yes.
So like this.
Yeah.
There no, there are not stereocenters in this molecule. The reason is you're saying this carbon here,
Yeah.
this is an sp2 hybridized carbon, so it only has 3 things connected, not 4, and so it's not a stereocenter. And the other reason for that is because the reason for that sp2 hybridization is sp2 hybridized things are planar. They're planar, which means we always have a plane of symmetry going right through them basically like this, or in the board like this. So if you have a plane of symmetry, you can't have chirality, and that's why it has to be different.
What if it's a 2-bromo 1-cyclopentene, or 1-cyclopentene, but 1 pentene instead of a 1?
Instead of the diene like that, same issue.
I guess it would have to be
But you're right.
bromine.
So like that, right? Now we have a stereocenter. Now this carbon here is a stereocenter, and depending on whether we make a dash or a wedge, we can assign it as R or S. So let's try it.
Do one more time.
What? Yes. So let's pretend it has a wedge. What's the configuration there, and how would you name that compound? Okay, so in the interest of time, first of all, the name is going to be 3-bromo 1-cyclopentene, and we actually don't need the 1, but we'll leave it there just to be more clear. And then we're going to add our stereochemistry in parentheses. So what'd you come up with, R or S? It is R. There's only one stereocenter, so we don't really have to specify that it's 3R, but it's R. What? Did you say Y?
I didn't hear what you said.
Oh, I just said you don't have to put the 3. You don't have to say 3R because there's only one stereocenter. So if we just say R, we know it's referring to that particular one. All right, so one other thing that we haven't done exactly, but that I'm sure you can do, is to draw a structure from the name with the stereochemistry in it. So you can do that. But I want to look at one other thing. So what happens when you're looking at similarities or differences in compounds, and it's not immediately clear that you're really dealing with the same thing? So let's take a look at these compounds from the book. And this is where you can use this assigning configuration to really help you. Okay, so this is similar to what we did, but we can, the question here is a little bit different. What is the relationship between these two molecules? So the reason this is potentially tricky is that it's not drawn as clear, like it's not drawn as the same middle chain with just the dashes and wedges are different. You'll notice over on the, it looks kind of all flipped over, and then on the left, the methyl group is actually down, right? Like, or I'm sorry, it's pointed down, but it's coming out at you, whereas the bromine's over on the left. So at first glance, it really almost looks more like a constitutional isomer situation, like things are actually connected in a different way. But they're not. And we can verify that the same way we've done that for a couple chapters now, by looking at the longest carbon chain and looking where everything else is connected. So in this case, we'd go 1, 2, 3, 4, 5, 6 carbons. So we've got the alcohol on number 2 and the bromine on number 5. And then we can do the same thing here, because even though that methyl group is on a wedge, it's still part of the carbon chain. So that's still a 6 carbon chain with bromine coming off of number 5 and the OH coming off of number 2. So these are definitely not constitutional isomers. They're either stereoisomers, so enantiomers, diastereomers, or they're the same. All right, so one way that we can determine that is we can actually manipulate the structure to put them in a more similar place. So we can rotate that bond between carbon 4 and carbon 5 to put that CH3 back over on the left, and then we can flip the whole structure over and do all this manipulation. That's fine. We can just find the configuration of each stereocenter, and if they're the same, they're the same, and if they're not, then we can deal with that relationship. So let's do that. Find the configuration of each stereocenter in those molecules, and let's see what we've got. So carbon 2 and carbon 5 are the stereocenters. Determine their configuration, and then we'll see what we've got. let me show you the answer to these just for time, and I want to talk about a couple of things before we go. So all we need to do is assign those configurations. So this one should be 2s 5r. Yeah? Agree? Disagree? I might be wrong. Let's see. That's right. That's right. Yeah, that's right. And then this one is 2r 5r. Okay, so that answers the first part of the question, which is that these are not the same because they have different configurations. So what are they? What's the relationship between them? They're stereoisomers, but what kind? Are they enantiomers or are they diastereomers? Yeah, they're diastereomers. And how do you know? They're diastereomers because they're stereoisomers, but they are not mirror images. And the reason we know they're not mirror images is because mirror images would have the opposite configurations. So if the first one was 2s5r, its enantiomer would have to be 2r5s. All the stereocenters would have to be switched. But only one stereocenter is switched. Only the 2 is switched and the 5 stays the same. So that makes them diastereomers. Stereoisomers, but not mirror images, not complete opposites. Okay, so a couple of tools to help you out with this stuff. With the naming and with the R and S, with just the caveat that please don't cheat, because you do actually have to know this. But it is helpful to be able to actually check your answers. So if you look at, there are some chemical structure to name apps out there, such as ChemDoodle. It's web.chemdoodle.com. But yeah, chemdoodle.com is the site. So they have this little like drawing program and you can draw molecules and stuff. And you can, put stuff in there. And then it will actually name it for you, including the stereochemistry, so you can check it, right? And there's a bunch of these. You don't have to use ChemDoodle. There's a bunch of them out there that work. So, again, not for use on quiz problems, because it's a quiz, right? But when you're working on homework, when you're working through book examples, when you think you've got something right and you just can't figure out what's going on, if you think there's a mistake in the key for the homework or something else, it's good to be able to check your work with this stuff. So these programs can help you with that. All right, so I'll see you Wednesday. Lab, quiz is due on Wednesday. Wednesday's another technique-based lab about extraction. And then after that, we'll start in with more reactions. Yes?
So what did I do wrong?